There's something special about steam, and it's no surprise it started the Industrial Revolution. Now I've built LEGO engines powered by air, magnets, gravity, and even rubber bands. But there's one power source I've always wanted to tame: steam. The idea sounds simple. Boil water, spin a turbine. But when you try doing that with LEGO, everything changes. The heat, the pressure, the leaks, and the parts you think will survive don't. So today, I'm going to try building a turbine from scratch, one that works with real steam. And to pull it off, we'll need materials that can handle temperatures hot enough to melt normal plastic. Okay, so these two little guys here are both technically steam engines, but we can also simply power them with pressurized air. Now this one here is a single-cylinder piston engine, and this one is a turbine. You can hear this one achieve some insanely high speeds, and it's this kind of steam engine that I'm going to attempt to create today, while making sure it's compatible with LEGO. Now we could just make these two engines compatible with LEGO by printing some simple parts like this cup, which we can pop onto the LEGO engine here, and then pop the engine into the cup. With a little belt drive, there we go, a little piston engine that can drive a LEGO build. Right now I'm just using air so I don't soak everything just yet. Then of course we can use a slightly different printed cup to secure our little turbine engine in the same manner to our LEGO engine. We can hear this one reach some higher speeds than the piston engine at the same pressure, but at a little less torque. And this design does feel promising for this project. Okay, well this is fun and all with air, but can we get one of these running using steam? Now this one here is a little piston steam engine I bought on AliExpress, and the main reason I bought it was to use the boiler and the burners. My plan at this stage was to nick the boiler and these two burners here, and then attach them to a LEGO build to produce the steam we need. Oh, we can hear something. Little bubbles. Once the burner starts releasing steam, we can give the flywheel a kick, and off she goes. Hey! Now this engine is connected to a small motor, which is acting as a weak generator, powering these LEDs here, though fairly weakly. Uh-oh. So clearly, it absolutely is possible to build a small steam engine that can do a small amount of real work. But the real challenge is in taking the very weak jet of steam being produced here, and trying to get it to spin up a small rotor. You can hear the jet of steam being produced if I wave something in front of it, but I've got to say, it feels incredibly weak. In fact, even with this freely spinning gear, the jet of steam can't even get it to move, let alone a bigger rotor like this one. So step one of this challenge is figuring out what sort of rotor to make. This rotor, made of LEGO doors, can slot into a holder here, so that we can see what rotor shapes are more effective. Now I don't know what kind of pressure we'll get with steam, so I'm going to start off with some air pressure very low at about 10 psi. We'll attach our air just over here. These straight blades are not likely to be very efficient. We'll track this yellow dot here to see how fast it's spinning. Okay, let's see. Looks like around 2000 RPM at about 10 psi. As expected, nothing crazy. But this whole design is open and really not very efficient, so let's try something else. Now this rotor has curved blades to better capture the fast-moving air, while also reducing drag as it spins. And this time, we'll add an enclosure. And then this here will be our inlet. I can pop it just here. Now even though the tolerances are terrible here, and there are gaps between the bricks, in theory the enclosure can help to direct the flow of air around the turbine, improving its efficiency. At the same 10 psi, we definitely seem to be getting a significant improvement to the speed. Though I'm a little suspicious of the readout here, this doesn't sound like 11,000 RPM. But I think we can safely say the enclosure probably helps a bit. So let's design some parts to test our future turbine. The rotor will sit inside an enclosure like this, and the nozzle will inject steam or air. And then off it goes to the brand new Bamboo Lab P2S, with its gorgeous new large touchscreen which makes quick adjustments and diving into menus much easier and more intuitive. Having gotten comfortable with 3D printing on the A1, my brain has been racing, thinking of all the new things I can do to augment LEGO, like this steam engine. But for a while now, I've had no idea how to get the prints to survive the high heat. So when Bamboo reached out about their upcoming successor to the P series, I knew this was my chance. Now this guy can create things that have only been a pipe dream for me until now. You see, for now, we're printing these parts in standard PLA filament, But later, we're going to make these parts heat and moisture resistant so it can withstand the extreme heat and pressures of direct steam. So a big thanks to Bamboo for partnering with me on this video. This P2S has been a breeze to set up, and I love that it does all of its own calibration and tests and setup automatically. It even has advanced AI detectors for flagging issues like misprints and spaghetti. For high flow rate extrusion and real-time detection of filament clogs, the P2S has even inherited the new Dynasense extruder from its flagship bigger brother, the H2D, giving 70% more extrusion force. And for my smaller prints like these, the quick swap nozzle changes in seconds, getting even finer print details, which really helps for these small pieces compatible with LEGO. Now, with our tester designs printed, including this little vaned rotor, let's hook it up to the copper boiler.
Oh, this is probably a dumb idea. Something's gonna melt.
And we'll use just a single burner for this test. Okay, after a minute or so, we're starting to get a few gurgles from the boiler.
Oh, I think we have some liftoff.
Hey, what do you know? It seems to kind of work.
Yeah, we do. Oh, there she goes.
Though, unfortunately, I missed the key moment when this whole thing failed.
Stalling for some reason. That doesn't seem good. Oh, I think the inside's a little bit rusted. Oh, one of these things broke off. Okay, I've dried everything off here, and unfortunately this is a little bit worse than I thought. So what actually happened? Well, if I pop off the front of this thing, we can see the lid is quite warped. That's to be expected. And then as you can see here, the hot steam has melted the little nozzle input. So I'm assuming this thing here is completely blocked. As to be expected, the housing here is not really round anymore, it's quite warped. And then the turbine blades are all over the shop. Clearly can't handle the heat. Now the real problem here is the boiler. I think what happened is when this nozzle here melted shut, this little rivet here on the boiler popped off from here, and now we have a nasty little leak coming from this hole.
Wow, good thing Katie came to the rescue with this little pear-shaped flask. I printed a little holder for it, which we can then stick onto the flask to hold it at an angle above the burners. And we'll test it using this little piston engine. This cork will allow us to build pressure, and I'll use the same pneumatic tubing that I've been using in my air engine builds. Squirt of water, plug her up, and attach the tube to the engine.
Good to go. Got quite a bit of heat coming through. Oh, we're almost boiling, I think.
Now, unfortunately, I couldn't get this little engine to run, so perhaps the turbine will be able to spin up under lower pressures.
Okay, let's see if we'll have any better luck with this turbine instead.
Well, I suspect the condensation was causing the turbine to get clogged.
Looks like we have just a little bit of exhaust. I think we're not building up enough pressure. Now I'm going to guess this pipe is far too thick and we need to increase the pressure by making a nice small nozzle to push the steam through.
And this is exactly where we're going to start using the special powers of the P2S. You see, this stuff is special. This is PAHT-CF filament, which is made of carbon fiber.
Now you can see here, this one is rated for 260 to 290 degrees C. That's got a really nice texture.
And we're going to print 3 nozzles out of this stuff with 0.75, 1, and 1.25mm holes to see which works best with our steam boiler. Now these should be able to handle the heat.
Okay, we've got 3 different nozzles at 3 different diameters. Alright, let's first try the 0.75mm nozzle.
At 10 psi, let's see how close we need to get to push this light piece around.
Then the 1mm nozzle.
Now this one seems to create a far better jet.
And then finally the 1.25mm nozzle.
Okay, pretty similar. Next, let's see how they spin a small rotor. Now there are a couple of different designs we could use, like these vane rotors, but there's another type with buckets that I suspect will be even more efficient. This isn't quite a Pelton wheel, but the simple bucket shape should still work pretty well. Pop them into the cage here, and we'll measure its speed using our usual yellow dot.
Okay, off we go. Very gentle.
Now, a small hole like this allows us to build more pressure in the boiler, but as we can see, even at 10 psi, we're not getting much. So let's try our 1mm nozzle. As expected, so long as we can reach 10 psi, this produces a much stronger jet. And our 1.25mm nozzle? Well, that's very impressive, but we're very unlikely to build up 10 psi in our boiler with such a large nozzle. Out of interest, I did want to check that the bucket design is actually more efficient than the vaned rotor. And indeed, it does look worse.
Getting a whopping 290 RPM.
Our 1mm nozzle fares better, but still not as well as the bucket design. And the 1.25mm nozzle as well. They all seem to get around 30% less speed than the bucket design.
Okay, let's see if we can get this turbine to run on the 0.75mm nozzle. I hope this thing can still hold the flask. Ah, we're getting something through.
Steam is finicky. A smaller nozzle allows greater pressure to build.
Oh, nearly.
But it also doesn't allow as much fluid to pass through it. And this 0.75mm nozzle really struggles.
This holder melted slightly, so we're going to need to print that out of something heat resistant too.
Now this stuff here is PC filament, and this is what I plan to make all of my rotors out
That
of.
stuff is so white it almost glows. So this one is rated for 260 to 280 degrees C.
It's also a lot more affordable than the PAHTCF filament, but it's absolutely crucial that it's kept bone dry and totally isolated from the humidity in your room, which apparently is exactly what the AMS2 Pro is for. At this stage though, I didn't fully appreciate why the P2S has a door, and why the climate control is so important for these engineering filaments.
Yuck, look at all the spaghetti.
Fortunately, the AMS2 Pro has a dehumidifier heater built into it.
Now this PC filament really needs to be dry as a bone. So let's check inside the AMS to see what the humidity is like. Yuck, it'll probably drop a little bit, but it's setting at 46% right now. This is way too high.
So if we jump into the settings here, we can set it to dry out our filament overnight. We'll use the highest setting for PC filament and hit run, and we can also have it rotate the spools to dry them out more evenly. So it's slowly bringing the temperature up, and this will run for about 8 hours. Perfect to leave overnight. Well, it's the morning now, and we're apparently down to 16% humidity. That is a massive improvement. And there we have it, a perfect print. Without the climate control, this project would likely be completely impossible. So let's pop our flask into our new heat-resistant holder, and this time we're using our largest 1.25mm nozzle to see if it can produce a reasonable jet of steam.
Well, hey, we've liftoff! Excellent! Hey! Okay, at least we now know the turbine will work.
No joke, I was genuinely terrified I wouldn't even manage to spin a small turbine.
Clearly 2 of these makes a big difference. And after all that, this holder seems to be perfectly fine. No warping or anything that I can see. Very nice, this filament held up really well to the heat of the steam. Okay, let's try the slightly smaller 1mm nozzle. In theory, this should create more pressure. There we go, we're off. Very nice, I'm pretty sure this is spinning a lot faster. Yeah, it definitely is. Wow! That is awesome! Okay. Excellent.
Well, that settles it. The flask boiler is fit for purpose.
I was starting to get so stressed this wouldn't work at all, but this is excellent. I think the way this performed, I'm going to go with the 1mm nozzle.
And what speed are we getting with our 1mm nozzle, per flask, and 2 burners?
And we're off.
Now it takes a moment to heat up the pipe so that it produces mainly steam,
We're going higher, I think.
instead of condensate, at which point we get to around 1800 RPM.
Out of interest, what is torque like? Not as bad as I expected, actually.
But of course, still pretty weak. So, can we actually do something useful with this candle power? Well, if we fashion a basic tank out of these tracks and then power both sides with a central axle, maybe we can drive it? We'll of course need a hell of a gear reduction to improve torque, so hopefully this 75:1 gear reduction is enough. At least blowing it seems to work fine. So we'll chuck them together, and off she goes. Then we need somewhere to put our boiler and burners. Our burners we can pop into this holder here, and our boiler can sit right onto this axle. Our nozzle then can fit onto the side of the tank over here, and our cork will seal the whole thing up. Okay, the moment of truth. Does our steam engine actually work?
Well, it seems like it's trying.
It feels like it's close. When we lift it off the ground, yeah, now it works. But it seems it's a bit too heavy to run under its own weight.
Not quite enough torque.
It's still incredibly satisfying to watch it chug along when given some help though. And there's something about that whir and hiss that I just love. Okay, well, I bet I know how I can get this to run even under its own weight. Let's get rid of these tracks and simply pop on some wheels. There's a reason most vehicles use wheels. This has gotta make more efficient use of our power source. Oh, hell yeah, this is awesome.
Hey, she's off.
It's not very fancy, but I just find it so cool that this thing is able to drive itself using just the power of a couple of candles. I mean, it's not going to win any races, but just look at her go. I can totally see how steam power was a game changer, helping us to power all sorts of machines. Speaking of, why don't we up the ante and build something sort of steampunky that will be a real challenge to power? If we attach this leg to this mechanism here, now we have a leg that can walk. A credit here to the incredible LEGO inventor Sariel. I've borrowed heavily from his leg design on his website and it works magnificently. We can then add two legs together and add a pair to each side of this body. And now we have the beginnings of a sort of bug-like creature which walks when we spin either side of the legs. Our engine will need to hook up to the central drive chain, so rubber bands will make that easiest so we can modify the engine output as needed.
Alright, let's make our poor little dead bug here a bit stronger.
With two of these body segments added together, now we have an 8-legged bug-like creature that can hopefully support itself. But I'm not even sure yet if it can walk. So let's try it with a motor first. And yes, it does require some torque to run, but at least we know the rubber band belt drive has enough friction to drive it. It did take a bit of trial and error to get the timings correct for the leg movements, and I'm sure there's a more efficient way to coordinate them, but hey, it works well enough, I think. To improve the coupling with the belt, I also added some tensioners here on either side. And then, of course, we need a massive gear reduction. Our turbine has a very small amount of torque. Let's just try it real quick with a tester rotor, which we can pop onto the input here. And yeah, I can see the gears on our creature spinning slowly.
Oh, seems to work.
And with some pressurized air, it does indeed seem to run the legs okay. So let's get rid of our tester rotor and print off our new steam turbine. We're going to use our real fancy PAHTCF filament for the housing. It has these exceptional thermal and mechanical properties and is also totally stable when wet. Now this stuff is going to get real wet. So this housing has a 1mm nozzle built into it and it snaps right onto our LEGO build like this. Then we'll need our rotor, which I'm printing using this white PC filament. And this has been a major upgrade, being able to remotely check on my prints through the new high frame rate and high resolution built-in camera. So with our new heat-resistant rotor, we can slide it onto our metal axle, and now we have a fully steam-ready engine. Our boiler can slide onto this axle, and our two burners can sit into their holder here. The silicone tubing then fits snugly onto our 1mm input nozzle, and with some flame to our boiler, let's see. Well, it's definitely generating some steam.
Oh, we're off.
But even with some assistance from the lungs, yeah, it just doesn't seem to have enough torque to drive the turbine.
Well, at least the parts are holding up really well to the steam and the heat. Now, of course, this steam turbine's going to get hot, so we're going to have to use a metal axle. Okay, time to close her up.
So next, I wanted to see if closing off the turbine would help it produce better pressure and improve efficiency. I'm in two minds about sealing the turbine, as I suspect it'll collect water, creating extra drag against the rotor. But if it can be kept clear, it could improve performance.
Oh, she's off.
On my first attempt, it drowned almost immediately.
I think we might be getting waterlogged. So I'm going to try and orient this exhaust downwards so that the water can drain out. Okay, now the exhaust port is at the bottom here. We got some bubbles, and it looks like we're off.
This time we seemed to get an okay speed for a short while, but it eventually drowned itself again.
Still stalling. Okay, clearly for some reason this is not working well. This feels much harder to spin.
After clearing the water,
Now that the water is drained out a little bit, it does look like the friction is improving.
so perhaps closing off the turbine is not optimal with all the moisture building up.
Oof, yeah, this feels totally sodden. There's quite a lot of friction.
So let me widen the axle hole to try and reduce friction even more. And we'll run the turbine without the lid to see if it can run continuously with a mild gearing connected.
Okay, that seems a little better.
This is bound to run better than an exposed rotor without any housing. Okay, she's off. Not a crazy speed so far, but it does build as the pipes warm up.
See what the torque is like back here. Oof, not very good. Well, we're going higher.
After a minute or so, we started getting a much nicer speed, even going as high as 1900 RPM.
It's weird, it's cycling between going fast and slow. Right now it seems to be going kinda slow. And now it's speeding up again?
Any boffins here, please tell me why it sometimes cycles like this.
What on earth is causing this? Well, when it's left open, this casing stays beautifully cool. This makes me wonder if maybe some bearings would be a good idea to use here. Okay, I'm going to try print this housing again, using filament that isn't quite this fibrous. I feel like this is creating a lot of extra friction.
So, back to PC filament.
So this is PC filament again, just like the white one, and this can take 260 to 280 degrees C. So hopefully this will print just like smooth plastic.
Once again, we'll dry out the filament, and this was a longer print, so I stepped out and simply checked on it using the Bamboo Handy app. So, with our metal bearings in place, on goes our brand new turbine housing and rotor.
Yeah, that feels a lot smoother.
Now we're using the same material for both the rotor and housing, just different colours.
Yeah, we're off.
It should withstand the heat almost as well, while possibly reducing some friction at the axle hole.
Now we've broken 2000.
And indeed, we seem to have a small uplift in performance. Lastly here, I just wanted to check if closing the turbine using this new material and bearings on both sides improves performance at all.
Oh, we might have lifted off.
And you know, it was pretty weird.
Oh, sounds like it's struggling.
It did eventually get the highest speed, going all the way up to 2500 RPM, but it often then choked itself and dropped. So for the sake of consistent performance, I reckon I'm not going to use the fully enclosed housing.
Whoa, that is cooking. Well, I've got to say, these materials hold up to the heat really well. Not even any warping.
Now I'm sure there's some folks watching and wanting to see a Pelton wheel, which is famously efficient with jets of fluid. So here's a bigger turbine housing, which can take a bigger rotor. We'll pop him just here. And then here's a Pelton wheel, which I had to print a little larger to preserve enough detail. And this one seemed to spin beautifully with very little friction, though it is definitely heavier than our smaller bucket rotor. So let's see how it does.
Well, we're off.
It has a larger diameter, so in theory it could run slower, but with slightly greater torque than our smaller rotor.
Now, there is quite a bit of moisture leaking around the outsides. That's probably slowing it down a bit.
Alright, what speed are we at? Looks like just under 1200 RPM. Yeah, this experiment wasn't amazing.
Yeah, the thing is, I'm not sure I've got that sub-millimeter accuracy I need to make sure that jet of steam hits right in the middle of these buckets here. So I don't think we'll use this one.
But there was one more thing I wanted to try to improve performance. Surely adding a third burner will add 50% more power to the system? This boiler burner is the same footprint as our previous one, but should provide 50% greater output. However, interestingly, it performed almost exactly the same as our 2-burner source. So we'll probably need to find some other ways of improving performance.
Okay, I've increased the gear reduction on the turbine output just here, and added some rollers here for better power transfer. So now let's add our burners, and our boiler. Now we're starting to get some bubbles.
Come on, creature from the deep, you can do this. Let me give him a quick helping hand and clear some moisture. Looks like he still doesn't quite have enough oomph.
Ah, you know what? With all of this added, I think now his bum's just a little bit too heavy.
There is something we can do though. If we support his belly, we can see if he can at least still move his legs. And yeah, he's off. Now I have to speed this up to actually see his legs moving. And if you look at the boiler and burners, you can see how much he's consuming just to move his legs a few steps.
I'm delighted to see it's not actually producing much water. This is almost all steam now.
So yeah, this does work, but man, it consumes a lot of fuel for a pretty minimal amount of work done.
Well, we got through an entire boiler of water here, and I'm not even sure if this guy managed to take one full step with all of its legs. We'll have to see in the sped up footage.
However, we're not giving up. I have one last trick up my sleeve that I know for sure will work. This here is a bigger version of my bucket rotor.
Okay, I've increased the size of the wheel here in the output, so these legs should run quite a bit faster now.
We'll get rid of the small turbine, and we'll print a bigger housing for our big rotor. Now this nozzle is 3 times larger, and you'll see why.
Okay, we've got our new housing here with a fatter intake. And we've got our nice big rotor.
Now we're going to push the limits of what these prints can do. With this.
This beauty consumes 2,500 watts. We're going to dial from 0 to 6 to tell us how much steam we want it to produce.
We'll turn her up to just 1 on the dial. And it takes a second to heat up.
Honestly, even 1 is probably enough to power this turbine. Whoa, that's getting hot. And if we turn her up... Woo! Yeah, all over the place. Alright, let's try it on just 1 out of 6. Whoa! Nice, something tells me this will run just fine. Yeah, well, it works, but my living room is now absolutely soaked.
Now, I'm not sure the audio here does justice to just how violent the steam and turbine sounds in person. But here we have it, running our turbine with a small gear reduction and only 1 out of 6 on the steamer power setting. Just listen to her. I love that the fan is blowing the steam around, creating some nice vortices. Yep, this'll work just fine.
Oh, that is moist. Alright, let's give her some juice.
Okay, I think I can confidently say we have enough power this time.
Whoa, nice.
This is definitely more than enough power for this gear reduction. So in a second, I'll remove much of the gearing to get our creature to walk faster. For now, I'm just delighted he can support his own weight while walking.
Okay, I've removed a lot of the gear reduction now, so it should move way faster.
This puts a greater demand on the turbine, but I think we still have enough power to drive our creature. And this is real time now, with no speeding up.
I can barely see this thing.
I just love how this looks like a sort of swamp creature emerging from the deep and dripping water all over the place while it drags itself onto land. I've got to say, this was so incredibly satisfying to finally see a real steam-powered LEGO build, even if it is messy as hell. By the way, if you like experiments like these with LEGO and technology, feel free to subscribe or drop a like. Cheers! To be honest, I'm astonished you can just print parts that are resilient to this much heat, pressure and moisture. 3D printing is such a fun and useful way of augmenting LEGO builds, so if it's useful, I've put up my designs on MakerWorld in case you'd like to print them yourself. To be honest, they work even better with just pressurized air. Because let's face it, a 2500 watt steamer is probably overkill.
Well, at least the plants are getting a nice watering.
So if you'd like to pick up your own P2S printer to get these pro level prints without the pro pricing, or just get some filament, my link is below in the description. A big thanks once again to Bamboo for partnering with me on this project, and we'll see you in the next one.